We're going to be talking section 2.6 all about rational functions. Rational functions was a chapter in Algebra 2, so some of the things that we're seeing are going to be familiar. There's really one idea that we're talking about today that's new to you, and then one idea we'll talk about at the beginning of class tomorrow that's also new to you. So to go get ahead and get started with rational functions, we just want to understand what is a rational function. So rational functions, as you're jotting this down, remember they have the word rational, which has the math word ratio in it, and a ratio looks like a fraction. So essentially, these are functions that are fractions. Or fraction function. So we're defining it as a quotient of polynomial functions, and quotient implies division, which is fraction. And then this is notation that I'm going to use. So we're going to be talking about functions f of x that are rational. And then we're going to say they are some n of x over d of x. So make sure you're kind of on board with n of x and d of x. N of x is going to be talking about the polynomial in the numerator. D of x will always refer to the polynomial in the denominator. Because I'll use that on some different slides. Okay. And I put a little qualifier there that's really important, such that d of x is not equal to 0. Because if the denominator was 0, then the function would be undefined, and that would not be a very interesting function to look at. Okay. So also, something to keep in mind in terms of domain and range is domain is restricted by your x values that make denominators equal 0. So the number of x values that make your denominator equal to 0 is determined by the polynomial that is d of x, the polynomial in the denominator. If that's a linear polynomial, you only have one number to exclude from your domain. If it's a quadratic polynomial, you could have up to 2 numbers to exclude. Cubic would be up to 3. And if you'll remember, like when we exclude numbers in our domain, we do those like separate intervals. So like if we're going to exclude 2, negative infinity to 2, in union with 2 to infinity, all parentheses. If I have to exclude 2 and 3, then I'm going to have 3 intervals. Negative infinity to 2 in union with 2 to 3, the stuff in the middle, in union with 3 to infinity. So then you're skipping over 2 and you're skipping over 3. So if you add more, you just add more intervals to your domain. So kind of be aware of that. We're going to start by talking about the piece that makes you a pre-calculus student. So a lot of times when I'm teaching pre-calculus, I like to say, this is what makes you pre-calculus and not algebra 2. And you have extra knowledge. One bit of knowledge that most algebra 2 students don't know about are holes. N of x and d of x, if the numerator and the denominator share common factors, there is a hole in the graph at the 0 of the common factor. To find the y-coordinate, plug x into your reduced function. So you might want to note that when we're talking about holes, we're really just talking about a point that doesn't work. And a point would be labeled as an xy ordered pair. On the graph, we'll mark those points as holes by using open circles. So now you'll sometimes, instead of drawing a regular point, you'll draw an open point. And to get the x-coordinate of that point, that's this piece right here. The 0 of the common factor. So whatever factor you cancel from the numerator and denominator, whatever makes that thing equal to 0, that's where your whole happens. So we're going to look at this one, f of x equals x squared minus 1 over x squared plus 4x plus 3. Go ahead and in your notebooks, factor it as you think it should be factored. Numerator and denominator. Can you factor the numerator? Can you factor the denominator? Can anybody factor x squared minus 1? X plus 1 times x minus 1. Thank you, Maddie. And was anybody able to factor x squared plus 4x plus 3? X plus 1, x plus 3. Thank you, Dylan. What do you notice? They each have x plus 1. So I cross those out and I write whole exclamation point. Yeah. Exciting. Okay. Now, I actually want to find out where that hole is. So for the x coordinate of the hole, I'm going to set x plus 1 equal to 0. Whatever that factor was that I canceled, find that value. So that's x equals -1. And then to find the y coordinate of the hole, you have to plug the x into the reduced function. Okay. Note that if you were to plug it into the original function, we could look at the factored form over here. If I plug -1 into the first factor in the numerator, -1 plus 1 would be 0. If I plug that into the first factor in the denominator, -1 plus 1 would be 0. So essentially my numerator and my denominator would be 0. So if I plug it into the original, I would get something like f of -1 equals 0 over 0. And we don't even know what that is. Some people could argue it should be 0 because if the numerator is 0, the fraction is 0. And then other people would argue it's undefined because the denominator is equal to 0. We have a different name for that. We call it indeterminate. You don't know what it is. Unhelpful. So you don't want to plug the x back into the original function. You want to plug it into your reduced function. So we're going to plug it into x minus 1 over x plus 3 without the factor of x plus 1, the one we cancel. So for the y coordinate, I'm doing y equals x minus 1 over x plus 3, which is -1 minus 1 over -1 plus 3. So -2 over 2. And my y coordinate is -1. Now, I have a little statement here that follows. If there is a hole, note that the hole takes over the graph. Like there's not going to be a vertical asymptote there. There's not going to be an x-intercept there. There can be nothing else where the hole is. The hole is just that open point. Okay, so the hole takes over. That's why you do it first. If I were going to graph that, I would draw an open circle at -1, -1. Okay, any questions about the hole that you want to ask me? I'm going to copy this. Okay, so what makes you pre-calculus? You're going to factor first to look for holes. If you don't do that, then you're basically stuck in Algebra 2 where you don't want to be. Okay, you want to move on. Okay. After you do the hole, we're going to do all the things we did in Algebra 2. So I'm going to move a little bit faster through these, give you time to write them down, and then we'll look at some examples. So in Algebra 2, you did study horizontal and vertical asymptotes. You didn't have to worry about holes in Algebra 2, so you just always started with your vertical asymptotes, set your denominator equal to 0. Whatever makes your denominator equal to 0, that is going to be your vertical asymptote, unless you've already factored and found a hole. That can make your denominator equal to 0, but then it's a hole. For the horizontal asymptote, you compare the degrees of n of x and d of x. So remember, everybody's got to be on board this train, numerator and denominator. What do I mean when I say degree? Which exponent? The highest exponent. Okay. So if you need to jot down something in your notes about degree, if you don't know that that's the highest exponent, make sure that you write that down so you understand your notes. Okay, so you're looking at the highest exponents. So we're comparing the exponents of the numerator and the denominator. And then notice I'm using that notation again. If the numerator is less than the denominator, if the numerator is equal to the denominator, if the numerator is greater than the denominator. There's three cases. And these should sound familiar to you. At the very least. If the degree of the numerator is less than the degree of the denominator, as we go towards positive and negative infinity for x, the denominator is going to take over because it has more x's down there. It's got a higher degree. So then you're going to have really big numbers in the denominator compared to small numbers in the numerator, which will give us horizontal asymptotes at y equals 0. If the numerator and the denominator degrees are equal, they're going to, as we go towards positive and negative infinity, those things are going to be so big that they're going to kind of like the degrees that are the same, they're going to take over. But then the numerator and the denominator are going to be very close to each other in value, and so it's y equals a over c, where a and c are the leading coefficients of n of x and d of x. So if you have like 3x squared over x squared, as we go towards positive infinity, like that's always just going to be 3 over 1, the ratio of their leading coefficients. And if you have like 3x squared minus x plus 5 and 3x squared plus 4x minus 2, that other stuff isn't going to matter because infinity squared is so big, it takes over. If the numerator's degree is greater than the denominator's degree, you can say it does not exist. I use DNE for does not exist. You can put the null set, you can write none, you can write NA, whatever, as long as you tell me it's just not there. Side note, this is kind of a weird thing that will happen with some rational graphs. Your graph can cross your horizontal asymptote, which for some of us is a violation of the definition of an asymptote. It's supposed to be a line that we get really, really close to but never actually touch. However, you can cross it in the middle of the graph because horizontal asymptotes are really for end behaviors. Okay. So as long as on the far left and on the far right of your graph, you're getting close to that horizontal asymptote, you can cross the horizontal asymptote in the middle. Now, I put my example down here at the bottom. So we're going to go ahead and do the asymptotes for that. I'm going to see if I can get my graph. There's my graph. Pull that down from the previous slide. So we're going to find vertical and horizontal asymptotes here. The nice thing about rational functions that have holes is once you've canceled out the hole, you can just use your reduced function. So it makes it a little bit easier. When I'm looking for my vertical asymptote, look in the denominator. If there are any fractions left over, or factors left over, set those factors equal to 0. So we have a vertical asymptote at x equals -3. So I'm going to draw that. And when I'm doing my horizontal asymptote, I'm going to be comparing the degree of the numerator with the degree of the denominator. You can use the original, but you can also look at the reduced function. What do you notice about the degrees? They're the same. So we've got an equals, which should be y equals a over c. Those are the leading coefficients. So like if we're looking at the reduced functions, we've got x to the first in both of those. The leading coefficients are whatever's in front of x. So 1 and 1. So ours would be y equals a over c, which is 1 over 1. So we could say y equals 1 for our horizontal asymptote. So I'll go F1, and there's my horizontal asymptote. Now, if we had the same denominator but didn't have a whole, so if we had 2 factors in the denominator, we would have to set both of those equal to 0, and we could have 2 vertical asymptotes. So if you have 2 vertical asymptotes, you're going to have 3 parts to your graph, and you have to make sure you have a graph in each section. Okay, moving right along. We're going to need some extra points to draw the graph of a rational function, so I recommend intercepts. They're easy points to get, right? Nothing on this slide is groundbreaking. You already know this. If you want a y-intercept, set x equal to 0. If you want an x-intercept, set y equal to 0. So we can find the x and the y-intercepts. Let's do that for, I'm going to get my graph up here too, so we can keep seeing it. Let's do that for this function. And again, if you've already canceled out a whole, the whole is going to take over. It's not going to be an intercept or anything else. So you can just work with the reduced function. So if I was doing the y-intercept, I would set x equal to 0 in the reduced functions. That would be 0 minus 1 over 0 minus 3. Oh, plus 3. So that's negative 1 over 3. 0 and negative 1/3. Is it okay that my y-intercept is a fraction? For sure. Just go down a little bit, right? Okay, so I'm going to go down 1/3. About right there. For the x-intercept, do that down here, I'm going to set y equal to 0. So that would be 0 equals x minus 1 over x plus 3. How are you going to solve for x in that equation? Dylan? Okay, that'll be our shortcut. But if I wrote it out, like I just sub 0 in for y, what would you do to solve? Multiply by your denominator. You would want to get x out of the denominator, so you can multiply by the denominator. So we can multiply by x plus 3 on both sides. And then think about, if you've made y equal to 0, what's always going to happen when you multiply both sides by the denominator? It's always going to equal 0. It's always going to disappear. So we could really use what I would call a shortcut that Dylan gave us. The x-intercept is actually just the numerator set equal to 0. So if you want to write a little note up here, if you're comfortable with that, you can just set the numerator equal to 0 because that's the only way the fraction equals 0. If you don't like that, if that's too tricky for you to remember, then just write it out and multiply by the denominator every time. That works. So we have an x-intercept at 1, 0. Now, as I'm graphing my intercepts, my whole, my asymptotes, I'm getting a really nice picture down here, and I can probably guess what's happening. I'm going to come up and approach my horizontal asymptote. I'm going to come down and approach my vertical asymptote. You might be able to guess where the other branch is. It could be above or below the horizontal asymptote. So rather than just guess, I would pick an additional point. Okay. So to finish my graph here, I would do an extra point. I'm at -3. That's where my vertical asymptote is, so I might choose -4. And then you're going to be doing this without a calculator. but I don't mean this to be super challenging. So you can take your x value, you can plug it into your reduced function, so you have less x's to worry about, and then I always just write mine as fractions. So I just do the numerator. What's negative 4 minus 1? Negative 5. What's negative 4 plus 3? Negative 1. And then I look at negative 5 over negative 1 and I'm like, okay, that's positive. 5 over 1 is 5. So then I can go left 4 and up 5. Probably most of us would say that 1 point is enough. We know that that's now above the horizontal asymptote, so we could draw the rest of the graph. If you were feeling unsure of what the graph should look like, then you just pick an extra point. You could pick any point you wanted. Questions? Hannah. I picked a point. It's down here. I just needed something on the left of the vertical asymptote. The vertical asymptote is at x equals negative 3. I had no points over there, so I picked a number that was less than negative 3. You could pick any number that you wanted. And then I got those numbers, the negative 5 over negative 1, by simply plugging into the reduced function. So you can use x minus 1 over x plus 3. If you want to plug it into the original one, that's okay, but when you're without a calculator, it's probably easier to use the reduced. Now, before we leave this, let's just real quickly label our domain and range. So I had made a note that your domain is restricted by the things that make your denominator equal 0. So what things made my denominator equal 0? Negative 1 for the whole, the x-coordinate of the whole, and negative 3, the vertical asymptote. So the x-coordinate of the whole and the vertical asymptote are going to restrict my domain. So I would write it. Negative infinity. What am I going to meet up with first? Negative 1 or negative 3? Negative 3 in union with negative 3 to negative 1 in union with negative 1 to infinity. I'm going to have 3 sections. All right, what things are restricting your range here? Negative 1, because that's the y-coordinate of your whole. We went down 1, so there is no graph at negative 1, left or right. And the other thing that's restricting our range is our horizontal asymptote at 1. So we would do negative infinity to negative 1 in union with negative 1 to 1 in union with 1 to infinity. Okay, so you are, from domain, going to exclude your vertical asymptotes. You're going to exclude the x-coordinates of any holes that you have. For your range, you'll exclude y-coordinates of holes and horizontal asymptotes. But the range is a little bit different. It's only like you have to pay attention to your graph. If there had been a branch below the horizontal asymptote and I didn't have another hole over there, which I didn't find another hole, then I potentially could have had a value at negative 1. So I wouldn't have restricted that. Okay? And would have been everything less than the horizontal asymptote. Okay? If your graph crosses your horizontal asymptote, like I said was possible, don't exclude the horizontal asymptote because then you have a point on the horizontal asymptote. So the range is a little bit trickier. You really need to pay attention to your graph. Is there an actual y value at that point anywhere on the graph? Because if there is, then it's part of the range. Now I'm going to do one other quick one just for extra example. You do have a homework assignment from the textbook. There is a question on tomorrow's quiz where you have to label these things, so we want to do extra practice. We'll do f of x equals 3 over x plus 4. Sometimes the easy ones are so hard because they're so easy. We might overthink. Okay, you're in pre-calculus now. So when you see a rational function and you're being asked to graph, what are you going to do first? Factor, check for holes, right? You now know about holes, so you're always going to do that first. Can you factor anything in f of x equals 3 over x plus 4 or x minus 1? No. So we don't have any holes. We can start with the vertical asymptote. Where's your vertical asymptote? X equals? Sorry? -4. You guys talk so softly, that projector is louder than you. That's how soft your voice is. Can't even hear you over a projector. Okay. Horizontal asymptote. We're going to compare numerator degree to denominator degree. First, let me ask this question. What is the degree of the numerator? 0. If you don't see an x there, it's x to 0. This is x to the first. So the degree of the numerator is less than the degree of the denominator, which means our horizontal asymptote is? That would be if it was greater. 0. Y equals 0. The denominator will take over eventually. So if we put infinity in here, infinity plus 4 is so huge compared to 3 that it's basically nothing. Okay, so that's why we have y equals 0. Let's see. I could do x-intercept. So we'll use Dillon's shortcut, set the numerator equal to 0. How do you guys feel about 3 equals 0? Not very good. I'd rather have $3 than $0. They're not the same. So that means there is no x-intercept. For my y-intercept, plug 0 in for x. So 3 over 0 plus 4, that would be 3/4. So I do have a y-intercept as 0 3/4. If you want to plug those things in like as a table of values as opposed to writing x-intercept, y-intercept, you could do that. And I'm going to see what I've got when I graph it. I'm going to go left 4. I'm going to go up or down nothing for my horizontal asymptote. I got 0 3/4 for my y-intercept. I'll probably need another point or two, right? So plot additional points as necessary. So I'm going to make a table of values. I might choose, like, okay, let me just see what's happening near the vertical asymptote. So I'm going to choose -3, and then I'm going to go on the other side of the vertical asymptote. I'm going to do -5. And see if these 2 points give me enough idea about what my graph is doing. So 3 over 1 when I plug into the function. So I'm going to go left 3, up 3. Okay, I think I know what that branch is doing, right? At -5, that would be 3 over -1. So I'd be going left 5 and down 3. You think you might know what that branch is doing? Hanging out down below in that corner, getting close to the horizontal and the vertical asymptotes. So I'd say you probably just need 1 point there. Now the ones where you might need extra points are going to be if you have like 2 vertical asymptotes. Because then in the middle, that's like the weird spot. Sometimes you have a U that opens up, sometimes you have a U that opens down, but sometimes you have that cubic sort of thing. And so to determine what it's doing, you need a few points in there. All right, what would we exclude for domain? -4, the vertical asymptote. What would we exclude for the range? 0, the horizontal asymptote. Okay, since we only have one thing to exclude, we only have 2 intervals right there. So there's a lot of things, hopefully a couple of them, like maybe the vertical asymptote you already know from Algebra 2. You are going to need to spend some time doing your practice problems tonight and then reviewing this information for your quiz tomorrow so you can answer some of those questions. Even if you make mistakes on tomorrow's quiz, it'll be in your best interest to have tried something on the quiz for when you get them back next week. So there's your homework assignment.